Okay, good afternoon. So let us start a lecture devoted to angular momentum. Probably not new to you, actually, I'm sure not new. You have already seen what we will talk about today, but once again, maybe it's good to repeat, as the ancient were saying. We also take this occasion to practically construct the spherical harmonics that I was discussing last time. Remember, in this corner of the blackboard, last time I said there are functions I call YLM, functions of the two angles, such that L square, which is the total angular momentum square, which has a complicated expression with derivatives with respect to theta and phi, this object is equal to h bar square, an integer plus 1 times the same function. So they are eigenfunctions of L square with this value for the eigenvalue, and also eigenfunctions of Lz, which never appeared in our Hamiltonian, which is with eigenvalue m, apart from h bar, where m goes from minus L to plus L. And L is an integer which would be 0, 1, 2. Okay? So all this, we already used it, okay? Although I didn't prove it to you. Now today, we're going to explicitly construct them, but we are going also to more generally argue on what any possible angular momentum occurring in a quantum mechanical framework would do, okay? So I want to put things in perspective. Until now, we have a single particle, for instance, in a central potential, and the orbital angular momentum was a very natural operator. But later on, we will encounter spin, which is also another possible source of angular momentum for particles that have spin, okay? More in general, if you have more than one particle, you can think of combining angular momenta of several particles or spins of several particles, or even combining orbital angular momenta with spin angular momenta, okay? So you can form more general objects that you can still call angular momenta, okay? And their common feature is that they obey a commutation rule of this kind. So let me call this more general angular momentum, just a second, J rather than L, just to put the things in perspective of a more general application. Whenever you have that the commutator of two of them just gives you the usual epsilon alpha beta gamma times the other. So explicitly, Jx commutator Jy is just I Jz and cyclic version of this. Then this is an angular momentum, okay? It's more general than that. By the way, as you notice, I have put here h bar to 1, really, okay? There would be an h bar here. But it's a simple mental exercise to deduce that putting h bar to 1 is really nothing but measuring all angular momenta in the natural units of h bar. In other words, if you have this angular momenta and you define j tilde to be j divided by h bar, okay? So the angular momentum divided by the natural unit, which is h bar, then it's very simple to prove, for instance, for this. Divide everything by h bar square. Okay? You see that here you get 1 h bar exactly for each one of this, and so you get j tilde of x commutator with j tilde of y. And on this side, one of the h bar goes, and here I have j tilde of z. Okay? So it's as if h bar was 1, okay? But the meaning is I'm rescaling all my operators and measuring everything in terms of h bar. Is this clear? Okay? So this is what. So with this in mind, you see here, I might divide everything by h bar square, and this would disappear, and divide this by h bar, and this would disappear. Okay? Which is a little bit more friendly. Okay? There are no h bars in the way, but you know that they are there, obviously. Okay? So if you allow me this, I would get rid of the h bars in the following discussion. Okay? And I will also omit the tilde. You should think of them as being already dimensionless operators. Okay? Now, as I said, L is an operator that respects this, but the spin will be another operator respecting this. Even the sum of the orbital angular momentum and the spin of angular momentum is an operator that people call the total angular momentum. We will discuss the meaning of this way of writing, because after all, these are operators acting on different spaces, and I will explain to you what does it mean to sum them, okay, in due time. Nevertheless, people introduce the total angular momentum being the sum of the orbital and spin angular momentum. And as I discussed before, you could think of many particles and having, therefore, indices on these particles, for instance, sum over the particles, and this is also an angular momentum. You see that if you have two angular momenta and you sum them, so suppose I have an operator, call it J1, and another operator, call it J2, both of them, three of them obviously, both satisfying this equation. If you sum them, then it's simple to show that even the sum must satisfy the rule. Okay? So, with this in mind, let us tackle the object of constructing eigenstates of these three operators. Okay? So I have Jx, Jy, Jz, and let's see what I can do. First of all, they do not commute. Therefore, it's very hard. In fact, it's impossible to construct common eigenstates of three operators that do not commute. If they do not commute, you cannot diagonalize them simultaneously. Okay? Nevertheless, we saw that there is another operator, which is J square, which is the sum of the squares of them. Okay? And this operator commutes with any of the three. Okay? We proved that for the L, but we didn't use, in fact, the explicit expression for L as differential operator. If you remember, we just used this commutation relationship. Okay? Therefore, the proof is identical in our case. I mean, there is no change, and you can prove that this is equal to 0, and this is also equal to 0, and this is also equal to 0. Okay? So, although the three operators do not commute among each other, there is a fourth operator, J square, that commutes, for instance, with Jz. Okay? Now, whenever two operators commute, I can always find a common basis of eigenvectors. I don't remember if we already discussed this or we will discuss it in the following. I forgot when we discussed about, probably we haven't yet discussed this theorem. Okay? We will encounter it later on, but let me just point to the idea of the thing. It's very simple. If I have an eigenstate, say, okay, let me write what I want. I want to construct eigenstates of J square, okay? Let me just indicate with two labels, okay? This will be an eigenstate of J square with a certain eigenvalue, which depends on this first label, J, okay? What I tell you is that I can also find appropriate combination of this object such that these are eigenstates of Jz with eigenvalue just m, okay, the subject. And I can do so because they commute. Now, what is the idea? It's very simple. If I construct a basis for the first operator, okay, so the first operator in the basis I have constructed is perfectly diagonal. This is a Hilbert space, so it's infinite dimensional in principle, okay? So this will be the first eigenvalue, maybe with some degeneracy, this the second eigenvalue, okay? But in the basis of its eigenstate, it's just diagonal, okay? The other operator, however, is generally speaking not diagonal in the same basis, okay? So in general, I should expect blocks, okay? Nevertheless, using the fact, we will do it, the proof we will do later on, or the idea of the proof. Using the fact that the two operators commute, you can show that this block here does not involve, I mean, essentially in this object here, okay, you do have a block which you can further diagonalize without changing the fact that this was diagonal, because they were degenerate eigenvalues of this, okay? So you can mix them in any possible way without really changing the fact that they were diagonal, okay? So in other words, even if they are not from the start diagonal, you can make them diagonal by mixing, okay? The simplest case of this is when these operators are non-degenerate, okay? So let me show the theorem for the simplest case. Suppose that I know that the first object has a non-degenerate spectrum, then let us prove that the second is also perfectly diagonal. Okay, so let us suppose that I have a certain vector, okay, and I know that there is only one value of the quantum number for the first, okay? So if I apply Jz to this object, okay, and I calculate J square of this, then this is, since they commute, also equal to Jz J square, okay? But this is equal to Jz times the value Fj, okay? So the value, I can put it out, and this is the thing, okay? Now, you see immediately that if the spectrum of J square is non-degenerate, then this object here, having the same eigenvalue Fj, must be essentially proportional to the same object, okay? So you immediately see that this cannot be another state. It must be the same state, okay? So that's the idea behind the fact that when two operators commute, they can be diagonalized together, okay? I don't want to spend more time at this stage. We can see more later on about, okay? So, I want to show you this with the following conclusion, that Fj must be equal to some j plus 1, where j is integer or half integer, and m is an index going from j minus j to plus j in steps of 1. Okay? So this is the statement of what we are going to show in the following. All right? Okay, so let us proceed with this construction. It requires a few steps. Neither of them is complicated, but please follow the ideas. Okay. First of all, rather than working with jx and jy, it is very convenient to define two new operators. One is this, jx plus ijy, and the other is j minus, which is the Hermitian conjugate, because this is not Hermitian. Okay, you see there is an I. Jx, jy, and jz are Hermitian, of course. Okay, so this is the Hermitian conjugate of that with a minus. Now, these two operators are very useful for a very simple reason. Well, first of all, obviously they commute, okay, with j square. That is obvious, right? Because jx and jy both commute, and therefore even their sum. But the more important property is the following. If you calculate the commutator of jz with j, for instance, j plus, you will find j plus, okay, with the plus here. If you calculate the commutator with j minus, you will find minus j minus, okay? This is very simple. Just plug into here jx plus or minus I jy, and then use the standard rules. So, for instance, jx commutator with jz jx is equal to I jy, and this is plus or minus I, the commutator of jz jy, which is minus I jx. Okay? So you see you have a combination of jx and jy, and if you do the right algebra with all these i's around and plus and minus, you will get this. Okay? Try to do it. Very simple. Now, why is this useful? Look at the following. I take a state Jm, which I postulate. Okay, this is the goal. Don't look at it. It's up there in the blackboard, I suppose. Okay. Actually, let me write it here. J square Jm equal to Fj Jm, where this is j plus 1, and jz Jm equal to m Jm, m minus j plus j. Okay, so I now erase this, which is the goal, from the central part of this board. Okay, and I assume that I have some state, let me call it just Jm, okay, which is an eigenstate of j square, okay, with some value of the eigenvalue, which I really still don't know how to predict, but there must be some eigenstate, okay? These labels are, for the time being, a bit arbitrary in some sense. I mean, m does not appear anywhere. I might call it phi, okay? I might call the state any name you want. The important thing is that it is an eigenstate of j square with some eigenvalue. All right, then I construct j plus, for instance, the same state, okay? If this confuses you, call it phi, okay? Let me construct j plus phi. And let me try to calculate jz of this thing. Then, since I can use now commutators to write this as j plus jz plus the commutator of jz j plus, right? Because after all, this is nothing but the same expression applied to the state. But now I know, oh, sorry, I am, okay. Suppose that this state phi has eigenstate of j square and eigenstate of jz. I know that I can construct state common to both, right? I just don't know exactly what the eigenstates are going to be, the eigenvalues are going to be, okay? There are two numbers. One is fj and one is m, okay? And that's the reason why it's a good choice to put somehow J and M there in the labels. Now, this object, when acting on the state, has a simple effect, right? It's an eigenstate of this, and so it gives me what? Gives me exactly M, the number, times the state. Okay? This object is a simple thing. It's just plus J plus. So it's a plus J plus times the same state. Okay? But this is a number, so it's M. So you see immediately that this object is nothing but M plus 1 J plus phi. What does it mean? It means that if I have a state which has a certain M, then that very same state, if I act on it with J plus, is an eigenstate of Jz with M augmented by 1. Okay? So in some sense, J plus plays a role of ladder. It makes Jz increase by 1. Let me draw here. I had some value for Jz, say M, and with J plus, I got M plus 1. I don't know if M is an integer, by the way, okay? I know just it's an eigenvalue, some real number. Might be pi. I know that I can form pi plus 1. All right? Okay. So let me just representate here J and M, because I guess you will not be confused by this thing. Now, by the way, this very same object, while it changes M by 1, it doesn't change J square. In other words, if I calculate J square of this very same state, okay, well, let's call it Jm, okay, then since J square and J plus commute, okay, then I can also write this as J plus J square Jm. But this is some Fj, we said, okay, so it's a constant which I can take out. Okay? So if you read it, it's telling you that J plus applied to the state, it changes M by 1, but it doesn't change J square. It's the same, you see? Okay? In other words, these two states both correspond to the same Fj if you look at J square. Okay? So the eigenvalue is a given Fj, and is not changed by J plus. Okay? Is this clear? Now, you can repeat the thing with J minus. What changes is that you can still write this, identical, but what changes here is that this is equal to, well, this becomes a minus, but this is now J minus with a minus in front. You see here the minus? Which means that this object here becomes a minus. All right? So J minus has the opposite role of ladder operator down. Okay? So it decreases M by 1 rather than increasing it. Okay? So is it clear? I point on a certain eigenstate, which I assume has a certain M and a certain Fj, and I discover that by acting with J plus and J minus on the state, I can increase or decrease M by 1, while Fj doesn't change. They are still eigenstates of J square with the same eigenvalue Fj. Okay? In other words, I have found a certain degenerate group of states for J square. But I can repeat this process further. Okay? So if I now apply J plus to this state which I have formed, I can go on and form M plus 2. And here I can go on with J minus and form M minus 2. And so on. Okay? Apparently forever, right? So in some sense, it looks like I'm constructing an infinite ladder of states, all eigenstates of j squared with the same value, fj, which I still don't know, and all related to the initial m by this ladder, +1, +2, -1, -2. Okay? Still, I have doubt on this. And also, I'm puzzled by the infinite nature of this ladder. In fact, this cannot be true. Let's see why. Consider the following thing. I mean, it is true that the ladder exists, but what is not possible is that the ladder goes on forever. The ladder must terminate at a certain stage. Let me show you this. I erase this. So until now, the statement that I can make out is that J plus of a certain state is a state with a +1 there, while the Fj is the same, okay? Well, in fact, there is a normalization constant here in front. I didn't prove that the state was normalized. In fact, it's not normalized. This normalization constant, generally speaking, we'll calculate it later on, is some function of j and m. Similarly, j minus decreases by 1, and there is also a normalization constant in front. Okay, now, consider the following. J square, written here. I can write it as jz square plus the square of the sum of x and y. You can prove very easily by inverting these two things and plugging into there that this can also be written as 1/2 j plus j minus plus j minus j plus. Okay? It's a very, very simple thing. So just substitute, for instance, here jx plus ijy, here jx minus ijy, and here the same, jx minus ijy, and here the same. And you will see that the terms with jx square survive in the 2, and in fact there are 2 of them, and with 1/2 you get this. The term with jy square also survive because you have I times minus I, it's a plus, okay? And they sum together and you get this. And the mixed term, okay, don't. They cancel between this and that. Okay? It's a very simple exercise. All right. Now, suppose that I calculate for instance, Jm, j square minus jz square. Okay? So I take the expectation value of j square minus jz square on the state Jm that I have selected at the beginning. Remember when I... Okay. Now, it's pretty obvious that this must be a positive quantity. Why? You see immediately, this is essentially the sum of the square of jx square plus jy square. Another way of seeing it is just using this expression. This is equal to 1/2 jm j plus j minus jm plus j minus j plus jm. Okay? Now, you see that these are not Hermitian operator, but when they go to the left, they become j minus jm, j minus jm. Okay? So in some sense, this is the norm square of the state j minus jm. And similarly here, sorry, this is j minus j plus. When this goes to the left, it becomes a j plus, and so again, this is j plus jm norm square. Okay? So you see that this must be non-negative. On the other hand, this object has this as eigenstate. So the value of this is equal to Fj. The value of this is minus m squared. Okay? So what this is telling me that for any m, okay, which I can pick up as eigenstate of Jz, then Fj minus m squared should be positive. But now you realize that there is a contradiction with the fact that m can increase forever. If m could increase forever while Fj stays fixed, sooner or later I would have an m so big, okay, that would be greater than Fj, all right? And this would not be possible, okay? Because this forces me to have m squared less or equal than Fj, okay? In other words, I immediately, given Fj, which I still don't know, there must be a cut here, okay? And the cut here, positive and negative, beyond which I cannot go with the ladder, okay? Therefore, there must be some value, let me call it m max, and some value here, m min, such that if I act on this with j plus, I should get 0. And similarly, if I act on this with j minus, I should get 0. 0 as a state. In other words, this forces me to state that there must be two particular states. One, I call it j m max, and one I call it j m min, which have the following property. J plus m max is equal to 0, and j minus m min is also equal to 0. Okay? Otherwise, I would increase, and this is not possible beyond a certain bound. Okay? Well, let us use this. Now, I'll show you that I can, in fact, have a very definite prediction for Fj. Let's see. Let me calculate j plus, j minus, j plus, j minus, j m max. Okay? Now, this object is 0. Okay? So if I apply this to 0, 0, I mean, just 0 in the Hilbert space. So not the vacuum state, I mean, just 0. Okay? Now, this should remain 0, because applying any operator to 0 is just 0. But on the other hand, it's a simple matter, okay? For instance, from here and from simple commutator to argue that j minus j plus, okay, I write it here, j minus j plus is just equal to j square minus jz square minus jz. Okay? This is quite simple to prove. Okay. For instance, well, directly, okay? You can, let's do it here, okay? So j minus is jx minus I jy. J plus is jx plus I jy, which you can always write as jx square, plus, from here you get jy square, okay? then I have a term that is plus I jx jy from here. And from here I have minus jy jx. Okay? But this is nothing but the commutator of jx and jy, and therefore it's I jz. Okay? So this is equal to jx squared plus jy squared minus jz. On the other hand, this, we read it from here, is just j squared minus jz squared. Okay? So you get this. Is this clear to everybody? Okay. Now, I substitute here, and I get j squared minus jz squared minus jz. And here I get immediately, when I operate on j and max, these are all eigenstates, all eigen operators of this object, right? This one has fj. This one gives me minus m max square. And this one gives me minus m max times j m max. But this must be 0. But this is a state. So how can a state be 0? The prefactor must be 0. Okay? And now, finally, I have cornered down what fj must be. Fj must be m max squared plus m max, or if I write it differently, this. You agree? Okay? Now, here I solve the mystery of the label. Why did I insist in calling this object j and not fj? Because after all, I want now to call this object, I give it a name. I call it j. Okay? So this famous object here, this largest integers that I get, I give it the name j. Okay? It's the maximum possible m that I can get. Let me call it j. And you see that immediately fj is a function of j, but it's not just j. So it's j plus 1. Okay? This is the reason why I didn't really use fj here. It was a bit asymmetrical notation. Is this clear to everybody? Okay, I can repeat the same spirit of proof in the other case. Okay, let's do it. This one. This time I have m min, and this time I operate with the minus and then plus. The minus gives me 0, and the plus cannot do nothing else but remain 0. Now I have the opposite thing to use, j plus, j minus. So I have this and this. And you see that these two things do not change, but this object here changes into a minus. And therefore, this object changes into a plus. Okay? So the opposite thing are almost the same, except for a plus. Is it clear to everybody? Now, I can calculate the thing. Okay? And immediately, I conclude that fj must be also, sorry, there is a plus, must be also equal to m min times m min minus 1. You see it from here. If I equate this to 0, I conclude that this must be true. But fj, I know it's equal to j plus 1. So can you tell me what m min must be, therefore? You see immediately that if you plug minus j here, I get minus j minus 1. The minus goes away, and everything is correct. Okay? So m min is nothing but minus m max, which was called j. Okay? Good. We're almost done. We have proved that the ladder, all of eigenstates of the same value of j squared which happens to be this j plus 1, must terminate at the maximum possible value of m being j, and the minimum possible being minus this j, okay? And it's a ladder of objects in steps of 1. Notice, still, I don't know if they are integer. This must be still pi plus 1, plus 2, or whatever. And this is whatever. I have no conclusion until now that this is an integer. But now, you can argue with me about the integer or semi-integer nature of this thing. How? Huh? Right. These are integer, okay? So I go from minus j to plus j into an integer number of steps. Therefore, they cannot be so strange. I mean, in some way, 2j, which is the difference between this and this, must be an integer. You realize, right? So 2j must be integer. Okay? So this cannot be pi, because this has to be the opposite of this, and there must be a certain number of integer steps connecting the two. And therefore, 2j must be an integer, which means that j can be either an integer or a half integer. Okay? So for instance, the simplest case is j equals 0. Okay? If j equals 0, there is not much. There is only one state here. M is equal to 0, and fj is equal to 0. Okay? This is our angular momentum 0, the S state. We already found it. Okay? A single state that has Lz equal to 0 and L square equal to 0. We'll construct it in a second. Now, let us do the next non-trivial thing. Okay? The next non-trivial construction has j equal to 1/2. This means that there are two states, one with m equal to minus 1/2, and one with m equal to plus 1/2. Obviously, they are connected by an integer, a plus 1, you see. Both have the same fj being equal to 1/2 times 1/2 plus 1, 3/4. Okay? Two states with the same j square and different jz. For j equal to 1, you have three states. They have 0, plus 1, and minus 1. Now I have an integer ladder. Okay? All three have fj equal to 1 times 1 plus 1, 2. J equal to, the next would be 3/2. Has four states that are minus 1/2, plus 1/2, minus 3/2, plus 3/2. Okay? Still steps of integer, as you see, and all with the same fj, and so on. Okay? So you see the number of states, depending on j, increases. In fact, it's 2j plus 1. You see, if for j equal to 1/2, I have 2. J equal 1, I have 3. J equal 3/2, I have 4. Okay? So in general, 2j plus 1 states in the multiplet. This is called a multiplet. Okay? A multiplet which has exactly the same j square and a changing by steps of 1 jz. Okay? So this is what we were willing to show, and we have shown in pretty general form using only the commutation rule and not so much the explicit expression of those operators. Okay? Now, obviously, they still apply to any object, for instance, also to L square. However, you must immediately notice, one thing before I jump to L square. Let us, since we have already used many, in particular, I erased the other expression, but I have here J plus J minus, which was similar. And it was this, okay? So let us consider this fact about normalization, okay? If I have a certain state, Jm, suppose it is normalized correctly, so the norm is 1, and I apply J plus. I know that I obtain a state that has m plus 1. But the point is, what is the constant in front that I have to put to normalize it correctly? Okay? Let me call beta this constant. Okay? Let us try to calculate it. So what you can do is immediately is that beta modulo square j m plus 1 j m plus 1. I take the scalar product of this object with itself. This is 1, okay? So this is just beta modulo square. On the other hand, this must be equal to j plus jm, scalar product with itself. But you know that when I take the bra, I must remember that the j plus becomes a j minus. I have to take the Hermitian conjugate, in some sense, of the object, okay? So this object here now, I have it there. So this object I can calculate. This is j square minus jz square minus jz. In fact, the very same calculation we have just done to prove that, for instance, fj was equal to that. And therefore, I can calculate that this beta square is nothing but j plus 1 minus m squared minus m, which I can also rewrite as j plus 1 minus m plus 1. Okay? So what I have to put, for instance, here, in order to normalize things correctly, is a square root of j plus 1 minus m plus 1. Okay? Is this clear to everybody? Now, in principle, I might add an arbitrary phase, okay? But, I mean, most common choices of phase are such that this object is just defined in this way. You see immediately, by the way, that this, if m is equal to the maximum possible value, that is j, and I try to calculate the right-hand side, I will get here square root of j plus 1, minus j plus 1, which is 0, okay? So the square root has two purposes, that of normalizing correctly the thing, and that also of telling you that if you go to the top state of this multiplet and you operate with j plus, you get 0, all right? Which is quite nice, okay? Now, you can repeat the game with j minus. This time you expect again to find m minus 1, and in the square root, you have to calculate the thing. Let's do it quickly. Let's see. I have here j minus. Here I will get j plus. And here I will get, now from this expression, j plus 1 minus m plus. You see, there is the last becomes a plus. Okay? So I do this, and I get this. So the thing is almost the same, except for a minus there. All right? And once again, if I apply this to the state with m equal to minus j, so j minus of j and minus j, I get square root of j plus 1, minus j minus 1, okay? And you see that this gives me just 0 again. You compensate all the minus sign, there is an extra minus, and this cancels that. All right? So once again, two purposes, normalization and getting 0 beyond the bottom. Okay? So this completes our story here. Here there is a square root, okay? Let's write it better. There is a square root of j plus 1 minus m plus or minus 1. j m plus or minus 1. Okay? Good. Now, this story about the ladder will be very useful in constructing the spherical harmonics in 5 minutes or so. Okay, so we will keep using the same strategy, but this time to construct explicitly the various states. Okay? So let us comment now on the possible value of L here. Here you see you have all the integers in the table I said, and you see a clear missing object. Here j could be integer or half integer. Now the half integers are missing. Why is that? This is pretty simple. Consider LZ. What should I erase here? Well, for the time being, that's fine. So remember that LZ is the only operator that has a very simple expression to remember, in fact. Rotations around Z are generated by the derivative with respect to the angle phi that describes, remember the, okay, maybe I should draw this again. So in spherical coordinates, a certain point is given by the angle theta, the angle phi, and obviously the radius, the distance from the origin. Okay? So phi, if you change phi, you just rotate around z. And it is a nice feature that Lz is just the derivative. It looks like a momentum with the phi as the coordinate that you take the derivative. Huh? Well, L as the h bar, then I divide it, okay, and this goes away. Okay? But this is a matter of choice. Okay. Now, what does it mean to be an eigenstate of Lz? It means that it must be a function of, in general, theta and phi, such that if you apply this operator, so you apply minus I, the derivative with respect to phi, you get the same function times what? Times m, where m is any number between minus j and j. Now, what I want to argue with you is that m must be integer and not half integer, for instance, as it would if j was half integer. Why? Let's calculate the solution of this object. You see, it's very simple. It involves only phi, theta is just a spectator, and I know how to solve it. It's the usual plane wave-like solution, right? The gradient equal to some constant. So the solution is some function of theta, I don't care because theta is a spectator, times e to the I m phi. You see, I take the derivative, I get down I m times minus I, just m. All right? So plane wave. But now you see, if you change phi and you add 2 pi to it, okay? So the same point here, I can regard it as phi plus 2 pi it shouldn't change nothing, right? Because 2 pi is just a full term. But let us calculate the function at phi plus 2 pi. You have same p of theta, e to the I m phi plus 2 pi, which is equal to the old function, so p theta e to the I m phi, times e to the I m 2 pi. Now, if m is an integer, this is just 1, because it's an integer number of 2 pi's, which is always 1. But if m was, for instance, 1/2 or 3/2, this would be a pi, or a pi plus, 3 pi, and so on. And this is very bad, because it means a change of sign. It means the wave function, if you consider it at phi or at phi plus 2 pi, which is physically the same point, has a different sign. This is not possible, obviously, okay? You realize I'm not doing anything except that I'm regarding the same point as phi or phi plus 2 pi. In other words, those wave functions should be single-valued when you return to the same point. Okay? And in order to do so, m must be integer. Okay? Which means that L must be integer. Okay? Now, this applies to orbital angular momentum, not to the general. Spin will not do this. Spin, in fact, characteristically changes sign when you do a rotation. But we'll see this later on. Okay? So if this is clear, let us start constructing now explicitly the spherical harmonics. The simplest case, obviously, is when L is equal to 0. L equal to 0 means that the only possible value is m equal to 0 also, right? There's one state only that we want, and it must have m equal to 0. So if m is equal to 0, this is just 1. On the other hand, I want a function of theta such that, for instance, L plus and L minus both are 0. Now, if you go back into your notes and you look for the expression of, for instance, of L plus, we wrote the expression of Lx and Ly, and you can sum them with an I and calculate what L plus is. L plus, you will discover, is e to the I phi minus I, the derivative with respect to theta, plus the cosine of theta over the sine of theta, the derivative with respect to phi. Okay? Now, let us take, therefore, the candidate spherical harmonics that has 0, 0. We already discovered that it cannot depend on phi, okay? Because it has m equals 0. All right, therefore it must be a function only of theta. Therefore, take now L plus. I know that this object must give me 0. As L minus also must give me 0. But let us calculate L plus. So this derivative has no effect because there is no dependence on phi. This derivative is telling me that I, e to the I phi, minus I, the derivative with respect to theta of the prefactor p of theta should also be 0. So this should be 0. Okay? Which means that the function must be also constant in theta, not only in phi. In other words, the function, as a function of theta and phi, is just a constant. No dependence on theta and phi. Now, you usually pretend that these functions are normalized. How do you normalize a function in the full solid angle variable? You do it in the usual way like this. You have an integral over d phi from 0 to 2 pi, an integral over d theta from 0 to pi, but remember that there is a sine theta in the measure, okay? And then you want that y, L, m, theta, and phi just give you 1. This is the normalization that you choose for all those functions. Now, if this is a constant, the integral is very simple. How much is this integral of, just 1 over the angle? 4 pi, right? The solid angle measure is 4 pi. It's a very simple integral to do. Therefore, this quantity here must be 1 over square root of 4 pi. Okay? This is the S state spherical harmonics. A very simple thing. Okay? Now, let us proceed with a more general L. Let me not do one by one first, but suppose that I have a generic L. Yep.
Plane wave obtained from the gradient and those obtained from the second derivative. Because here we get plane wave, but with the Schrödinger equation.
No. I hope, okay, the question is if there is a difference between the wave function obtained with the plane waves obtained with just the gradient and the Laplacian type of thing. Now, I don't want to cause confusion in your mind. I'm just noticing that this equation here is formally the same thing as P psi equal to K psi, okay? Where P is minus I h bar, the derivative with respect to x, which has, obviously, e to the I kx as solution. So formally it's exactly identical. Although they refer to different variables. This is a variable in 1D. This is an angle, okay? Also, the Laplacian is the p square. Here, Lz square is second derivative with respect to phi, but it's not the whole Laplacian. So please accept the analogies, but don't make too much confusion in your mind. What do you see? One is phi, the other is x. I don't think it's very profound in this respect. It's a very simple thing. They are same functions, but in different spirit. Okay? Now, the fact that this is not a free particle, okay? This is not a free particle. It's a particle in a potential, but it's free to rotate in some sense, okay? And in this free rotation, something similar to the free particle emerges, but only in the angle. But don't push the analogy too far, because then you would say, okay, then theta, what do I take for theta? E to the I theta? E to the, no, it's different, okay? So this free nature shouldn't be pushed too far to suggest that maybe this function of theta is also of the type e to the I k L theta. That would be wrong, okay? So please accept the analogy, but don't push to the degree that it gets wrong, okay? Okay, now, let us see. Suppose that I have L here, and I want M equal to L. So I am constructing the top state here for an angular momentum L, where obviously the top M will be just L. So I'm identifying, obviously, A, L, and J now. Okay, now, this equation is exactly identical, except that I have L here. And therefore, the solution will be some p of theta times what? Tell me what? L phi. Okay? So I know the dependence on phi will be I to the L phi. And here, in principle, this function might depend on L. Do we agree on that? Okay? That is very simple. But now I want to I want to determine this object here. How do I do it? Well, here there is a trick. You know that if I apply L plus to it, so if I do L plus of this, what should I get? 0, because that is the maximum possible LZ in the multiplet. Okay, but L plus has this expression, where now I shouldn't forget about this piece. So let us apply it. I have I e to the I phi, then I have minus I, the derivative with respect to theta, which I can operate on P only, you see, times obviously e to the I L phi. And then I have plus the cosine of theta over the sine of theta. And then I take the derivative with respect to phi, which brings down IL, e to the IL phi. Okay? Now, you can take out e to the IL phi, in fact. Okay? So you just put it here, e to the IL phi. And you notice that this object here, in principle, should be 0. So the I is really not important as well. So what you have is a differential equation for this that must be obeyed. The derivative with respect to theta should be equal to the cosine of theta over the sine of theta times L. Oh, by the way, here there is still the PL. I shouldn't forget about the PL. Okay? This seems a very difficult differential equation. After all, we are used to the ones, okay? Derivative equal to a constant. Here, derivative equal to a constant, but multiply cosine over sine. You see, now, not a simple plane wave. We must somehow work a little bit more. Let's see. A guess on what might be. L brought down, it means that there is some power to the L, right? But on the other hand, there is also a cosine. It means that this function, which is, okay, means some function of theta to some power L, when you take the derivative, you get L times L. But then you have to take the derivative of f, which somehow brings a cosine. Okay? Let us see. Suppose that I have a sine to the power L. When I take the derivative, I get L, the sine to the power L minus 1, times the cosine. But the sine to the power L minus 1 is equal to L, the cosine, divided by the sine to the power L again. Okay? So you see immediately that indeed this object is the one that reconstructs the power L totally. Okay? So you now know the solution of this. The solution of this is PL is some constant times the sine of theta to the power L. Okay? So as you see, not a plane wave, although it's still free motion in rotation, at least. Okay. Now, obviously, the normalization constant can be calculated. After all, you have to impose this integral to be 0. The integral in phi is very simple because the modulus square is 1, so the integral gives me just 2 pi. And the integral of d theta sine theta to the L, you must do it, to the 2L, in fact, you must do it. And if you do it, you discover that this CL is 1 over 2 to the L factorial, the square root of 2L plus 1, 2L factorial divided by 4 pi. Okay? It's a rather ugly looking expression, which I will never remember, obviously, and you probably don't need to remember either. But you know that in principle you can normalize this object. Okay? Now, in fact, there are several conventions on the faces of this wave function. After all, they are complex objects. And one of the most commonly used convention, in fact, puts here a minus 1 to the L. Okay? So a sign. Sign in the sense of plus or minus 1 in front of everything. For reasons that are very difficult to say in just a few words. I mean, there are books on angular momentum, by the way, where all properties of angular momentum are analyzed in all possible details, and everybody has certain convention. The most commonly used, I think, is this. Yep.
What's the reason behind this?
Beyond the minus, on the plus?
Yeah. Is it just like a convention, or there is something behind that?
It's, I mean, mostly a convention in the sense that depending on what signs you put, certain formulas come easier without minus, and certain. I mean, if you use a certain convention, this convention will propagate in a lot of algebra. There is a lot on angular momentum that, I mean, really, books, entire books on properties of wave functions. You can sum these functions. You can multiply several of the 3J symbol, 6J symbol. Really an amazing algebra behind this topic. So depending on how you choose some signs, obviously you will have plus or minus somewhere where, for instance, you don't like them. Okay? So in order to eliminate the signs from some place, you put it in a. I mean, a single sign is not physically measurable in some sense because the expectation value is always modulus square.
Yeah, because if we try to normalize, we'll get the CL plus the minus 1 raised to F.
Obviously,
Yeah.
obviously. In fact, you can put any phase in front, okay, in principle. Obviously, once you select a phase in this state, then all the other states have a definite phase, okay, because I will show it to you in a second, okay? But the phase that you put there in this first choice is a bit arbitrary in some sense, okay? Yeah.
Usually, when we normalize, we have the modulus square of a constant, and then here we have 1, for instance. Okay, we have something here. We 1, and then when we take the modulus of c, we just take the square root, and then we usually take the real part, right? We omit the imaginary part. And why? I mean, why?
The question is, when you normalize things, for instance, when we did this calculation here, also we had beta modulus square equal to this quantity, and we took here the positive square root of something. In principle, I might take a negative sign, or even worse, I could put e to the I 3 pi over 2. Nothing forbids me from doing that. It's a phase. Now, first of all, if I select a phase for a certain state, all the states that are generated by that state by application of some operators obviously will inherit that phase. So it's not that I can always choose phases randomly, because there are certain things that still have to be respected. Nevertheless, a certain phase ambiguity is kind of natural. You might say there are experiments that can measure this phase. It's a very difficult question, and to answer properly, I should probably know a little bit more. I think that the only possibility is that if there are interference effects between two states, okay? Two states belonging, by the way, not to the same multiplet, because otherwise they would have the same overall phase, okay? So two states having really a different phase choice, when they interfere, you will measure the phase difference. I suspect that in most cases, this is not really measurable, but I must admit that I do not have now a really perfect answer for your thing. There are phase effects that are measurable. For instance, Berry phase is a measurable consequence, a measurable phase. So one should not be very naive in saying, oh, phases don't matter because I always take modulo square. I mean, interference is one thing that can happen, and Berry phase is another major manifestation of a phase that is macroscopically important. So let me close the answer here without really giving you a full answer, but I think, yeah.
I didn't understand why you took L plus y0 equals 0.
Why?
L plus, the operator L plus,
Ah.
and harmonic spherical
Equal to 0. Oh, this is crucial. Good that you asked. The question is, why did I write that L plus LL, YLL is 0? Where?
The first one. The first one you took L plus y0
Ah, when I consider L equals 0. Well, if you put L equals 0, this is the 0, 0. In other words, for L equals 0, the 0, m equals 0, is also the topmost and the most, I mean, it coincides with these two extremes. Okay? So whenever you apply any JL plus or any L minus, you should get 0 immediately. There is only one state. Any attempt to go further up or further down gives you 0. Okay? This is the extreme case of a multiplet composed of a single state.
This operator cannot create
No, not for L equals 0. For L equal 1, if you start from 0, you create up to 1, you go down up to -1, and then if you operate on this, you get again 0. And if you operate on this, you get 0. So depending on L, you can go a little bit, and then you get 0. How much? 2L plus 1 states. All right? So if L is 0, just 1. That's the reason why for L equals 0, I wrote that this was, well, in fact, it's the same equation, you realize, except that now L is 0. Yeah.
One more question. When we say 0, do we mean a state with 0 eigenvalue or
No, 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 no. 0 is
just 0?
0. Okay? It's not a particularly fancy thing. It's a wave function that is 0 everywhere, and therefore it's really not a physical state. You cannot think of this as a physical state. 0, as we know it, is in every Hilbert space, because you can multiply any state of the Hilbert space by any complex quantity, but in particular 0 is a complex number. It's the simplest one. So 0 is there everywhere. But it's not a physical state, obviously, because there's nothing in it. I must not explain this to you. Okay. What else? So is this clear? So we have constructed now, in this way, states which have this form, PL of theta, e to the I L phi, where this PL of theta is some constant times sine of theta to the power L. Okay? Obviously, for L equals 0, you get just the usual constant, 0. L. Sine theta to the 0 is 1. All right. Now, what do I do with it? I mean, after all, I want all of them. I want the y, L, m, for m going from minus L to L, not just 1. Okay? So I have constructed this object, and I want this, until I get to, say, y, L, minus L. So I have to construct 2L plus 1, or 2L more states. How do I do it? L minus. Okay? So I know what L minus is. If I write L minus, I get this. I get the minus here. I get the plus here. And the rest is the same. Okay? So what I have to do is to take this state here, apply L minus, and what do I get? You might say, I get y, L, L minus 1. With what coefficient? It's written there. Okay? The coefficient is square root of L, L plus 1, minus L, L minus 1, if you read it properly. Okay? So in general, I should be careful. I mean, there are coefficients in front. Okay? But the calculation is a very trivial calculation. I have this function. You see, is sine theta to the L, e to the I L phi. And I have to apply an operator that I have there in all its beauty. Okay? So nothing could be simpler. I don't have to solve a differential equation. I have just to take a couple of derivatives. And I can do it. And then I can repeat the thing. I can take L minus 1, which I now have, just constructed, so to speak, in spirit, and I repeat the thing, and I calculate L minus 2 by just so I have L minus 2. Something like this. Okay? And I calculate L minus 2. I plug it to here, and I calculate L minus 3, and so on, until I calculate them all. Just to show how this process goes, let us apply it to the L equal 1, which is the smallest possible case. So the first state, the 1, 1, is just equal to this, where P1 is a constant times the sine. Okay, now I calculate L minus of 1, 1. I have, let's see, the square root of 1, 1 plus 1, minus 1, 1 minus 1, times 1, 0. Okay? So this is just a square root of 2. Therefore, y 1, 0 is just 1 over square root of 2, the application of L minus, which is I e to the minus I phi I d in d theta plus cos theta sine theta d phi applied to the function that is constant times sine theta to the power 1 times e to the I phi. Okay? Is this clear to everybody? Okay. Now, you see that I have the C1 divided by root 2. Let's see. I have, if I take the derivative with respect to phi here, I get just an I times the same object, okay? But you see that I have sine theta that cancels sine theta, and this gives me, therefore, a cosine theta times this I, the C1 I've got rid of, times e to the I phi. When I multiply by e to the minus I phi, this goes, and the I and I gives me a minus 1, okay? So if I have done things correctly, this will give me a minus cos of theta. Let me check. Okay. Yes, it looks right. What about the other term? When I take the derivative, I have again an I. There is another I, so another minus. And now I have a derivative of the sine that gives me the cosine. And I have e to the minus and e to the plus that again cancel. So I have really a same term, factor 2. So the thing is minus square root of 2 C1 times the cosine of theta. So there is no dependence on phi, you see, which you should expect, because m is equal to 0 there. So therefore, it's like having e to the im phi with 0 there. So no dependence really on phi. And the dependence on theta is now cosine rather than sine. If you repeat the process once again, you obtain a function that is very related to this, except that there is a minus here. Okay? So the function, I write it for you. The function 1, 1 minus 1 is equal to, by the way, this coefficient C1, okay, you can calculate it. Okay, where is it? It's here. This was equal to square root of 3 over 8 pi. And remember that it was minus 1 to the L. Okay, so there is a minus in front. If you use this thing here, this becomes a plus. The square root of 2 gives me 3 over 4 pi, and then I have the cosine. And finally, if you apply again L minus, you get this expression for y minus 1, which is 3 over 8 pi sine theta e to the minus I phi. Notice there is an opposite sign here, okay? So this is like the start of that, you see? But there is also a change of sign, because after all, the first initial sign, minus, has propagated and forced me to take here a plus, okay? And once I have here a plus, I apply L minus again, and I get a plus even in this thing. So you see, the choice is not that every time I choose another factor, it's then fixed by the form of L minus in some sense. Now, these three functions are what are called p-states. They look strange, probably to you, but if I write it better, you will probably start understanding what they are. So let me write y10 is, apart from this 3 over 4 pi, the cosine of theta. Then y11 is minus 3 over 8 pi, the sine of theta, e to the I phi, which is cos phi plus I sine phi. And y1 minus 1 is 3 over 8 pi sine theta cos phi minus I sine phi. You start recognizing a few things. Remember what happens in spherical coordinate. X, y, and z are given by r times cos theta. X is r sine theta cos phi, and y is sine theta sine phi. Okay? So you see that here there are the ingredients of x, y, and z. And indeed, if you take appropriate combination, for instance, if you sum those two, well, if you subtract it, because there is a minus here hiding, okay? So if you take, for instance, this minus that, and you divide by square root of 2, you get sine theta cos phi, okay? And if you sum it, divide by square root of 2i, you get sine theta sine phi. In other words, by appropriate combination of these two objects, you get states that, I mean, this object, you can call it the state pz, and you can form here a state px and a state py. These are Cartesian p states, okay? These are spherical p state. Those are Cartesian. They have no i's in them, and they have just sine and cosine, all right? Now, if you open up a book where they talk about this thing, they will probably draw for you, we are quite late, things like this. For instance, the PZ, they would draw something like this, depending on how nice they are pictorially, okay? Perhaps with the plus and the minus here. What does it mean? Okay? It means that the amplitude of this function, or if you want, if you take the modulus square, the probability, but then obviously the sign would not matter, is mostly localized in those regions. In fact, you can see that these are so-called, I think they're called polar plots. So you draw a point that is proportional to the value of the function in that direction you take. So you decide the direction, for instance, theta and phi. And you draw a point that is proportional to the function you want to calculate. For instance, for theta equals 0, it's a maximum. The cos theta is just 1. Okay? You increase theta and you reduce the function. But obviously it doesn't depend on phi, okay? So this function is totally symmetric in this way. And as you reduce theta to pi over 2, the function should be 0 because the cosine is 0. And then you keep increasing theta and you get again a cosine, but now with negative sign. Until you get to theta equal to pi, you get minus this, okay? So you see the meaning of this plot. It's just a polar plot of the cosine, nothing more, all right? And if you open the same books, obviously you will notice that they will draw px exactly identical to this, but just along x, and py along x. That is not strange, obviously. They are nothing but rotations of this thing, okay? As z is a rotation, if you rotate z by pi over 2, you get x or y. In the same spirit, if you rotate pz by pi over 2, you get px or py, okay? Now, exercise for you to do exactly the same game, but now for L equal 2. And you will find the D states. The D states are 5 of them, okay? So you will start from the topmost, which is the 2, 2, okay? Which should be sine theta squared e to the 2i phi with some constant. And you apply L minus until you get to y2 minus 2, okay? And then you will see that there are essentially squares here and there of sine and cosine. You can combine things in order to recognize again x, z, and y, and to form Cartesian d-states, which are the ones that are drawn also in the book, and they are pretty bizarre things like this, okay, with a belly here, or things like this, okay? This time, obviously, there are plus, minus, because there are squares of things around, okay? These are pretty useful, in fact, in thinking about also electrons in transition metals, for instance, because the sign of those lobes, okay, will determine, for instance, I mean, if you take an electron in this orbital and you have another orbital, you can calculate, depending on if the orbitals overlap or not, if there would be a good overlap integral or not. There are several arguments that you can think if you really have a visual feeling for those orbitals in the crystal, okay? So they're useful for the practitioners in the field. Please try to do this exercise. Okay, I think we are done with angular momentum. And next thing that I want to discuss is a bit more on symmetries. Until now we have been very, we haven't gone really in any detail on what is the meaning of a symmetry, but obviously we have used already those symmetries. We have used at least in two instances. One is when we did problems like the finite square well. Remember, there were odd functions and even functions. Why only those and not a mix of them? This is related to parity. The other case where we heavily used it is hydrogen. Okay? Using the symmetry, which is rotation in that case, we were able to, in fact, solve the problem completely, starting from a quite complicated three-dimensional Schrödinger problem. Okay? So we will learn that whenever symmetry is there, you can profit of it, because they will determine operators that commute with the Hamiltonian. And with those operators, you can try to diagonalize the Hamiltonian better, okay, in a faster way. Okay, so see you tomorrow.